Hello friends, welcome to our channel friends. And yes, today we are going to discuss about the Debye's theory. Yes, obviously we have already seen two parts or two videos of this concept only, and yes, we are going to continue this concept in the today's video also, because yes, the derivation part is little bit lengthier, and that's why we will make three, and more probably one more video will be again based on this video, this particular concept, because it is long derivation. Okay, so within 1 or 2 minutes we will just recap whatever we have seen in the last two videos regarding this concept. Okay, so according to Debye's theory, or before that we have seen two theories. One is classical theory and Einstein's theory. So whatever may be the drawbacks according to Debye in those previous theories, that those drawbacks Debye has overcome in this particular theory, right? So these actually two major drawbacks according to Debye in previous Einstein's theory and classical theory. They have considered the common frequency to all the oscillators, and moreover they have considered the independent vibrations of each oscillator, each atom. So every atom is act as an oscillator here, and they have considered each atom is vibrating independently. So yes, according to Debye, how it is possible? It is not possible, because each and every atom is bonded together with some different atom, and therefore we cannot consider their independent vibrations, right? And again, instead of taking a single frequency, Debye considered a range of frequency, right? And yes, again one more thing, what Debye has assumed is that a crystal can have number of modes of vibration, right? Because each and every particular atom is vibrating with some different frequency, therefore we may have the number of modes of vibrations, right? And the number of modes of vibrations per unit frequency range he called as the density of modes, denoted by Z of nu. So in the first video, whatever we have discussed is about to calculate the density of modes. So to calculate the density of modes, we have considered one dimensional thing first of all. Yes, already we know solving a one dimensional problem is easier, and then we will generalize for the three dimensional. So in one dimensional, let us consider a string is vibrating of length L, and for that then we have considered the strain equation, then Young's modulus, then compared and found the force at other end, and once we got the net force, then that force we have compared with the force according to our Newton's second law. Yes, and by equating those two forces we got one equation, and yes, in that equation y, that is Young's modulus, divided by the density, we called it as the velocity of propagation, right, of the string, or velocity of the wave. And finally we got this equation number 7, dou 2 u by dou x square is equal to 1 by vs square, dou 2 u by dou t square. Here vs is nothing but velocity. And if you look into the equation 7 carefully, this is a standard wave equation, and yes, its a solution according to our standing wave solution. We can write it as a sin n pi x by L cos 2 pi nu n t for one dimensional, right? And yes, if it is the solution of equation 7, it means that we should this equation 8 should satisfy equation 7. So for that purpose we will substitute here, and let us find dou 2 u by dou x square. So initially we found dou 2 u by dou x square. Similarly we found the dou 2 u by dou t square, means double derivative of solution u with respect to time. And yes, after substitution of these two values in equation number 7 or 8, sorry, in solution, then, or sorry, in standard equation 7 is, yes, this is what the 7 equation. So we got one formula, that is in terms of frequency, nu n is equal to n vs divided by 2l, equation number 11. So here vs is velocity, l is the length, n is what the integer, more or positive integer, n is always greater than or equal to 1. So from that we got some frequency values. For first n is equal to 1, this is the vs by 2l, then 2 vs by 2l, and so on. And from this we got, yes, whatever may be the frequency values, it is always in multiplication of vs by 2l, the basic frequency or the first frequency, fundamental frequency. Okay, and yes, we can say where our frequency spectra is a discrete spectra. Discrete means, yes, we have separate values, individual values, does not have any range of values. So that is what we call the discrete spectrum, we know. And yes, we can draw this frequency spectra like this, frequency on x-axis and the density of mode Z of nu on y-axis, and we got equidistant lines, because each and every line represents one this vs by 2l. And if we take the difference between any two successive, this v2 minus v1 or v3 minus v2, always we got this one vs by 2l. That's why all the lines are having same separation, equal separation. Okay, right. I think we have seen up to this in first video. In the next video, then we have continued. We have taken that frequency equation again, equation number 11, and by rearranging, we have written in terms of the n. So n value. And yes, after writing that, we have taken the derivative. dn is equal to 2l by vs, and d nu n, 2l by vs is constant. So this dn is what? The number of modes. And yes, up to this we have considered, and then finally let us consider, we have to generalize this for the three dimensional, because whatever may be the number of modes or whatever may be the system we are talking about, it is not a one dimensional. Actually, one dimensional is not a existing system, it is only for our understanding purpose. So we if you remember, initially we consider only dou to u by dou x square is equal to 1 by vs square dou to u by dou t square. That is for one dimensional. Now we will generalize for three dimensional. That's why we got one more additional term, two more additional terms in the left hand side of equation number 7, that is dou to u by dou y square plus dou to u by dou z square. So this is a three dimensional wave equation, and now yes, again we have to write its solution. Yes, we by taking the analogy from one dimensional only. In one dimensional we have written this sign term only, sign which contains only the x factor or x term, yes or no. Now two more additional terms, sign n. Now again here nx, ny, nz we have to mention separately. Earlier in one dimension only nx, that's why we have written directly n. So here ny pi y divided by l, which is corresponds to y axis, and this sign corresponds to z axis, cos 2 pi nu nt as it is. This is the solution to equation number this 14. Okay, again these nx, ny, nz are the positive integers. Now if we substitute these values of u in 14, again we will get the whatever may be the solution. So again we will write by analogy, it's pi square by l square, nx square plus ny square plus nz square. If you remember, for the one dimensional we got the similar equation. Here it is pi square n square divided by l square is equal to 4 pi square nu n square divided by vs square. So here we will write in three dimensional we don't write the nu n because it corresponds to x, y, z. So we will write generally nu. And instead of now here in one dimensional it is only n square, but now here it is for one dimensional. So for three dimensional nx square plus ny square plus nz square. So by taking analogy, or we can say by similar manner, we have written equation for three dimensional instead of doing much more complicated calculations. So if we cancel pi on both sides and rearrange, again if we write in terms of the nx square plus ny square plus nz square, we can write, take this l square to that side, 4l square nu square divided by vs square, equation number 17. Okay, now this equation gives the possible modes of vibration, because n value actually gives you the modes of vibrations, and the integers nx, ny, nz determines the possible frequencies. Okay, now in order to determine the number of possible modes of vibrations, z of nu, d nu present in a frequency range nu to nu plus d nu. Yes, what is our frequency range? Nu to nu plus d nu. D nu is the, let us consider, change in frequency, and nu is the original frequency. So that is what the range, nu to nu plus d nu. We will consider the network of points in the space. Now we will consider a space, moreover a three dimensional space here, and in this we will consider, yes, the three dimensional space, and in this space we will consider the number of points. So let us consider the network of points, we can call it as, right, as like our lattice. So we consider the network of points in the space defined by three positive integers. So that points are, or those points will be decided, their coordinates will be decided by these three positive integers nx, ny, nz, right? Means any point in this space will be governed by these positive integers nx, ny and nz. If you have to write the coordinates of any point, so you should write in terms of nx, ny and nz. That is the meaning. Okay. Now the radius vector, now let us consider a single point here. I will consider one of the points, so this point for our observation. So the radius vector drawn from the origin to that point will be r, and that r is, or r is the radius vector, but in terms of our nx square, ny square, we can write that as r square. So nx square plus ny square plus nz square is nothing but r square. So what is actually r? R is the radius vector drawn from origin to that point. Okay, and yes, that is equal to what? From equation 17, 4 l square divided nu square divided by vs square. So that is what equation number 18. right hand side we have written as it is. So this is the equation of sphere. If we look carefully, this equation represents the equation of sphere. And when we say the sphere, so obviously it's a volume we can write as 4 by 3 pi r square. Okay, so if we see this, I will draw one more diagram here. If this is the space, sorry, uh, yes, right. So now imagine this is a sphere, a three-dimensional sphere. Obviously sphere means three-dimensional. Okay, so one of the point we have observed of that, which will be represented by the coordinates nx, ny and nz. So that point, if we join from the origin, so that represents the radius vector r. Okay, and now this is sphere, let us consider its volume will be v dash. If radius is r, so v dash will be the volume of sphere, we know 4 by 3 pi r cube. Yes, so the volume of sphere, very basic formula. Now if we differentiate this equation number 19, then dv dash is equal to 4 pi, the derivative of r cube is 3 r square, right? Derivative of r cube will be 3 r square. So this 3 and this denominator 3 will get cancelled, and yes, obviously 3 r square and dr, because r is again a function of nx, ny, z or x, y, z. So therefore 4 pi r square into dr, this is the derivative of the volume dv dash we can write. Now the number of modes present in the frequency range nu to nu plus d nu, that is what our target we have to find, should be same as the number of points lying in the volume interval v dash to v dash plus dv dash. Yes or no? Let us consider this dv dash is the change in volume, small change in volume. Okay, so if this sphere already have the volume v dash, and after by means of some what we can say, the change, the volume will be changes to the dv dash, then the range of volume becomes v dash to v plus dv dash, right? Or we can say if dr is the separation, that means I will just draw here. Okay, so let us consider this is the dr change, and yes, one more sphere we will draw. Okay, right. Yes, so yeah, now this radius, the sphere new radius will be r plus dr, and the range will be, this is the range. Okay, change range, this is what the dr change, and this is what the change of volume or change in volume dv dash. So finding the number of modes in the frequency range nu to nu plus d nu, again the frequency is changing in this duration will be d nu. So finding the number of modes in the range nu to nu plus d nu is equivalent to finding how many number of points are situated in the volume v dash to v plus or v dash plus dv dash, or exactly equivalent to the finding the number of points in the radius vector r to r plus dr. Okay, maybe it looks like a very longer sentence, but you can see, okay, very simple, in a simple manner. If this is what the change, this new shell we can consider, this is the change. So finding the number of modes means whatever the number of modes we have to find are exactly similar to finding the number of points lying in the volume, this volume, or in the range v dash to v dash plus dv dash, and that is equivalent to finding the number of points in the range, radius range r to r plus dr. Okay, right. Now since each point occupies one on an average unit volume in the space of integers, now this is the space of integers, right? But moreover we know that our nx, ny, nz are positive integers. That means we have to consider the space where all these nx, ny, nz are only positive. Now from this, can you say me, now this is not a quadrant, this is octant, right? We are not imagining the two-dimensional space, but the three-dimensional space. So if we are talking about this is quadrant, now in this octant only, not quadrant, in this octant only we have all positive values. Yes or no? We know that if we are talking about the two-dimensional, this one, yes, okay, we call it as first quadrant, second quadrant, then third quadrant and fourth quadrant if in two-dimensional. So we know that all both are positive in this first quadrant only. Now if we are imagining similar three-dimensional space, again here only nx, ny, nz all are positive in this octant. Now it is not quadrant, it is octant. So in this octant, that means, and yes, since our nx, ny, nz are positive, we have to consider the number of points situated in this octant only. So therefore, we have to divide whatever may be the volume, total volume, by 8, because remaining this 3/8 part we don't want, right? We want only 1/8 part of the space, because in that part only we have positive values of nx, ny, nz. I hope you are getting. Okay. So since each point occupies on an average a unit volume in the space of integers, the number of points present in the volume dv dash of the spherical shell is numerically equal to the volume of the shell, right? That is what we consider. So the number of points are exactly equal to the finding volume, and what is the volume we got in the shell? That is dv dash, that is 4 pi r square dr, that is equal to dr. But since modes of vibrations are always determined by the positive integers, the point already I have said, but yes, of nx, ny, nz only, we must consider the number of points lying in an octant. Why this octant has been only considered? Because remaining 3/8 part of the space will have one of nx, ny, nz negative value, right? Not all. In the last octant we have all negative, but in remaining 3/8 remaining 3/8 means except the 1/8 octant where we have all three positive, remaining either one of them is negative, either one of them is negative, and that is not allowed, because our nx, ny, nz all are positive integers, and therefore we have to divide, or we have to take only this 1/8 part, means this volume should be divided by 1/8, right? So thus the number of possible modes octant defined by these positive integers, thus the number of possible modes of vibration, this dn is nothing but now z of nu d nu is dn, and that is equal to 4 pi r square dr, but divide by 8. Why this is divided by 8? Because one of the octant will only give you all positive nx, ny, nz. Yes, right. Now finally substitute the value. So I have written this 4 pi by 8 as it is, first term as it is 4 pi by 8, and what is the value of r square? If you see from equation number, where what is that equation number? I think 18 or not, r square, yes, equation 18. What is the value of r square? 4l square nu square by vs square. 4l square nu square, see here, 4l square nu square by vs square. Okay. Now again, what is the value of dr? What is the value of dr? Actually, what we will do is, here I will write the equation 18, r square is equal to 4l square nu square vs square. So what will be the value of dr? Here we will write, take the derivative. Yes, after taking the derivative, yes, what we will get, 2l divided by vs, 2l divided by vs into d nu, because see here, if we take the square root of, because each and every term is a square, so that's why its square root will be r 2l nu divided by vs, and if we take its derivative now, after taking the derivative, dr is equal to 2 as it is, l as it is, l is constant, vs in the denominator will be as it is, and the derivative of nu will be d nu. So this is the value of dr, 2l by vs into d nu, 2l by vs into d nu. Yes, right. So this is how we have substituted the value of r square and dr, right? Okay. Now let us cancel the things. Let us see what will get cancelled. Now this 4 into 2, 8, and this denominator 8. Shall I cancel? C. Yes, right. Now in the numerator, 4 pi l square into l cube, as it is in the denominator, vs square, and this vs again vs cube, and this nu square d nu I have written separately. Okay, no doubt. Now in a space, if we consider the l, now this is what, in one dimensional, the volume, the length of one dimensional string. But now when we are dealing with 3 dimensional, so here again we have the l, here again we have the value l along x, y, z axis, x, y, and z axis, right? So in one dimensional we are talking about the length, in 2 dimensional we are generally talking about the area, but in 3 dimensional we are talking about the volume. Now if I consider the space covered by these 3 lines, so it will be a cube of length L, and L cube is nothing but what? The volume of that cube, yes or no? So the volume of the cube will be L cube, nu square d nu. So we can write it as 4 pi V divided by Vs cube nu square d nu. And what is that? That is nothing but the Z of nu. And what is this Z of nu? These are the density of modes. Density of modes. Okay, so finally the first part of this article, or of this concept, is over. That we got finally the density of modes, and the density of modes here we found is Z of nu d nu is equal to 4 pi V. Why we have written V? V is nothing but the volume, and in the denominator Vs cube as it is nu square d nu. So here see, 4 is constant, pi is constant, and volume, if we are talking about a particular space, volume will be constant. Vs is what? The velocity, again it will be constant for that particular wave. So obviously the Z of nu and or the density of modes completely depends upon the frequency nu. Okay, so I think we should stop here. Almost this video also is making about 22 to 23 minutes. So yes, we will stop here, and the remaining things we will see in the next video. Till then, I suggest you please watch previous two videos. If you want, I will post that link of the previous two videos in the description box of this video, so that you will get the easiness for finding those videos. And yes, write your notes properly. Again, one more video will be based on this concept only, that is Debye's theory. Okay, and if you feel this is value addition to your knowledge, then like our video. For more such videos, subscribe to our channel Physics for You by Pawan Kachwe. And yes, if you want more videos, then yes, press the bell icon so that you will get the notifications of our next videos. And yes, thank you for watching this. We'll meet in the next video with the continuation of this concept only. Till then, you please take care and keep learning. Thank you. You'll get the two videos link of this previous this Debye's theory in the description box. Thank you. Thank you so much.